Okay, so a few more things in Chapter 10. Now, in Chapter 10, we had finished learning how to write or draw Lewis dot structures. We had finished knowing how to predict the shape of the structure, right? And we had also finished predicting whether or not the structure was, for example, polar or nonpolar, okay? And if you want to have kind of a review on that, and this is something I didn't mention, I should have mentioned, is tutors. We sent out a couple links about announcements about how to get a hold of tutors, but working with tutors and working in groups are generally the two indicators of somebody who's going to do really well in the class. Unfortunately, it's going to be harder to work in groups here under these conditions, but the tutors will always be available to us. So if you forgot how to make Lewis dot structures and stuff, it's not terribly important because this class, the exams going forward, won't have a lot of the stuff from Chapter 10 on them. But there are some fundamental principles that we need to make sure we have, because no specific questions maybe, but the understanding of some things needs to be retained or learned. We haven't given it to you yet. And the first thing is what we call hybridization. Hybridization. Now, what we talk about when we're talking about hybridization, what we're meaning is there's a problem with our Lewis dot structures, okay? If I want to draw a Lewis dot structure for this compound, right, CH4, and I want to think about, we know that the carbon is going to be in the middle, and we know that I'm going to have 4 hydrogens about it, right? Hopefully that brings back some memories about how to draw these Lewis dot structures, right? And maybe you remember, Camille, do you remember what the angle is here between those two bonds?
Is it the 109 point something or 120?
It's 109.5. That's right. 109.5. Very good. Is that angle between there? And we knew that simply because the 4 regions of electron density. Okay. Now, what is going on here between these carbons and these hydrogens such that you can have that angle? Because carbon and hydrogen, if we looked at an atomic view of just carbon itself, and we brought up our periodic table, what the periodic table here tells us about carbon is its electron configuration, right? 1s2, 2s2, or I should start with just helium. 2s2, 2p2, right? 2s2, 2p2. So that's our electron configuration for carbon. So what that means is I have an atom with 2 electrons in a 2s orbital and then 2 electrons in a 2p orbital. All right? So there's 2 electrons, and maybe I draw these electrons in, saying there's 1 in that lobe and 1 in this lobe. Now we know that there can be 2 electrons in each of those lobes, and we know that this lobe is empty. And those 4 regions, 1 extra electron in that lobe, 1 extra electron in that lobe, and then 2 electrons in that lobe. There's no electron density there right now. That's the bonding that's occurring when this carbon bonds with these 4 different hydrogens. Okay? So, let's see here. Are we still recording? I think so. All right. So, yeah, there we go. So, we could imagine in our minds a hydrogen, or not just 1, but 4 hydrogens bringing in their 1s orbitals, right? Because that's the electron configuration for hydrogen, 1s, bringing in their 1s orbitals and filling in these regions where there's a lack of electron density around this. This is our carbon there. Okay? And so we could think of a carbon. It's 2s2, 2p2, some missing electron density in that final subshell, bringing in 4 hydrogens with 1s to kind of fill that electron density. All right? But the problem is, if this was our imagination of what was going on, then the resulting angles wouldn't be 109.5, would it? What do you think, Alyssa? What would it look like would be the angle between this hydrogen and this hydrogen if this was the way the bonding was done? What does this angle look like here?
Maybe like a 30-degree angle, 45-degree angle.
Well, this is our, supposed to be at least, our y-axis, and this is our x-axis, and then there's our z-axis going back like that, right? So the angle between this lobe here on our y-axis and this one on our x-axis would be what?
90.
90, that's right, it would be 90. And the angle from this one here to the one going in the back, that would also be 90. And then this one to that one would also be 90. The only one that would, this one here to this one here would also be 90. The only difference would be this one here and that one in the back. What would that angle be, Preston? Can you see?
Yeah, just a straight line, 180 degrees.
Yeah, 180 degrees. So this is what we might predict based on our understandings of the electron configurations for these elements and forming a compound from them. But it shows us that it's not right, because we know, I've taught you at least, that 109.5 is the angles on these this molecule, specifically when there's one central atom with 4 ligands binding to it. So it shows us that something else is happening. Something else is happening, and we need to understand that a little bit. And what's happening is what is called hybridization. All right? And what we say is that carbon, where is it at? There it is. Carbon, with its desire to bond to 4 different regions of electron density, all right, what it does is it takes 4 of its atomic orbitals and forms these 4 regions of electron density that are not different in terms of their structure. They're all exactly the same. And to form these 4 regions, it takes those electrons from its available valence orbitals, right? So again, carbon is helium core, 1s2, 2s2, all right? And these 1s and 2s orbitals we can be reminded of these orbitals using an orbital diagram. Oh no, this isn't 2, sorry. This is 2s2 and 2p2. There we go. So we got the 2s here and the 2p2. Scoot this over a little bit. 2s and the 2p2. And what this CH4 molecule is doing, let me redraw it down here. The carbon is taking 4 of these, 4 of these subshells, or these orbitals here, hybridizing them together and producing hybrid orbitals that can reach out from the carbon to the 4 different hydrogens. Now, it had available to it, the carbon had available to it, 1 s orbital and 3 of these p orbitals. And it had 4 atomic orbitals available to it, and it needed 1, 2, 3, 4 hybrid orbitals to extend to the hydrogens. So it takes these orbitals, these atomic orbitals, puts them into a hat and mixes them all together and brings out 4 hybrid orbitals, okay? Now the number of hybrid orbitals we can know simply by looking at the compound and looking at the central atom and the regions of electron density around it. So there's 4 regions of electron density, so there's 4 hybrid orbitals needed. And once we know the 4 hybrid orbitals, we know that 4 atomic orbitals must have been required. So that means it took this s and 3 of these p's, okay? And the new hybrid orbitals, there's 4 of them, are not called s orbitals or p orbitals, but they're called sp3 in this case. And there's 4 of them. Whoops, sp3, sp3. There's 4 of these hybrid orbitals that are created. So essentially, carbon saw that it wanted to extend 4 regions of electron density. So it took 1, 2, 3, 4 of its atomic orbitals, mixed them together to make hybrid orbitals, and the resulting hybrid orbitals we call sp3 hybrids. And that sp3 name comes from the fact that we're mixing 1 of our s and 3 of our p orbitals. Okay? So, hybrids are made from the atomic orbitals that are around the central atom, and hybrids are named based on the number of the hybrid orbitals, or so if there's 1 s and 3 p's, then it's called sp3, and the number of hybrid orbitals that you need is determined by the regions of electron density around the central atom. Okay? So, I think you followed that per Harry? Harry, you think you got it? I'm going to ask you a question now, okay? So, here's a compound, carbon dioxide. All right? How many hybrid orbitals are needed for the carbon in this compound? How many hybrid orbitals are needed for carbon in this compound?
2.
2, that's right. Now, he knew that because he knew that the Lewis dot structure looks like this. Carbon, central atom, and then there's 2 regions of electron density. All right? So carbon needs 2 hybrid orbitals to extend here. All right? Now, what are we going to name those hybrid orbitals? I don't know, Harry. You have any ideas what we might call those 2 hybrid orbitals? Let's step back a little bit. Let's just remember that carbon, to make its hybrid orbitals, it has the 2s and it has the 2p. All right? And if it only needed to make 2, it only needed to draw on 2 of these, 1 of the s and 1 of the p. So the resulting hybridization around that carbon we say is sp hybridized. sp. Okay? sp because there was only 2 hybrid orbitals needed, and therefore only 2 atomic orbitals taken. Okay? All right.
Yeah.
David, if I had a central atom here, here's my central atom, and I have 3 regions of electron density. Let's say this is maybe sulfur dioxide, like that. 3 regions of electron density. There we go. What is the hybridization necessary around that sulfur there? How many hybrid orbitals does sulfur need?
Maybe
What's that?
2 or 3.
All right, 2 or 3 is right, with the actual answer being 3. Very good. So it needs 1, 2, and even though that's not a bonding region, it's still a lone pair region. So there's 3 regions of electron density, and that means that we need 3 atomic orbitals to come together to make 3 hybrid regions from that sulfur. Now, the sulfur is in a similar situation as kind of all the rest of our elements. I can bring up the periodic table for us to see it real quick. Whoops. Okay, so we have sulfur here. It has 3s2, 3p4. All right, so it has, just like carbon, an s orbital and 3p orbitals. These happen to be 3p, but it doesn't matter what they are. But how many of these atomic orbitals are we going to need here, David, to create these hybrid orbitals?
3.
3, that's right. So we're going to take 1 of the s's and 2 of the p's, and that's going to tell us the resulting name of these hybrid orbitals. What's it going to be, David? What's the resulting name? S
S
P,
SP, just SP.
sp2, right? Because there's 2 of the p orbitals that were needed. Does that make sense, David? Does that make sense, David? Did you follow that?
Oh, yeah. That,
Okay.
Thanks. That helped clear it up.
Okay. Very good. So, let's see, Aisha. What then, and this is the kind of question that we would be asked, what is the hybridization around ammonia? Now, I'm helping us out by drawing, ammonia, NH3. I'm helping us out by drawing the Lewis dot structure. But if we were asked what the hybridization is, we'd have to be able to draw the Lewis dot structure. After we drew the Lewis dot structure, we would count up the regions of electron density, think about the number of regions necessary, the number of atomic orbitals that nitrogen had to retrieve to create those regions of electron density, and then identify what's called the hybridization around that central atom. What do you think, Aisha? What is the hybridization around the central atom, around the nitrogen? And the answer is, answers are going to look like this. A, sp hybridized. B, sp2 hybridized. C, sp3 hybridized. Or D, sp3d hybridized. Those are our choices, Aisha. What do you think? Which one?
sp3.
sp3, that's right. This S means 1 atomic orbital of S, and the P3 means 3 additional, so a total of 4. And 4 atomic orbitals will be necessary to be used to produce 1, 2, 3, 4 regions of electron density there. Okay, very good. So that is our hybrid orbitals. Now, if a scenario exists like our carbon dioxide, let me get our carbon dioxide back up here. So here we have a carbon dioxide, the hybridization around the carbon. What is the hybridization around the carbon, Sarah? What is the hybridization around the carbon? Again, our answers are A, sp, B, sp2, C, sp3, or D, sp3d. Are you there, Sarah? Oh, she typed it in there. Very good. sp. Excellent. sp is the hybridization around the carbon in carbon dioxide. Very good. Now, what that means, again, is that carbon took an S and a P orbital, created 2 hybrid orbitals, and extended those hybrid orbitals towards those 2 oxygens. But it also means that these p orbitals were left behind on the carbon. These p orbitals are left behind on the carbon. Now, I'm going to do something wild here. Well, actually, I'm not going to do something wild. I'll just bring it up here. We have this drawing, all right, this drawing that tries to draw for us a carbon-carbon double bond, all right? So what we see here is, here's 1 carbon, and here's our 2nd carbon, and those 2 carbons are going to join in a double bond, all right? The compound that we're drawing here, let me draw that really quick. The compound that we're drawing is ethylene. It looks like this. Has 2 hydrogens coming off like that. All right, so if you can remember that, that's what we're trying to draw here. So this carbon-carbon double bond, again, who's next? Robert. Can you tell me, Robert, what's the hybridization around this carbon right here? What's the hybridization?
SP2.
sp2, that's right. 3 regions of electron density. 1, 2, 3. And so that carbon had to take an S and 2 P's to form those 3 regions. And this right here is a drawing. Those purple lobes coming out there are the sp3 hybrid bonds. One of the sp3 hybrid orbitals is extending towards this other carbon. One is extending towards this hydrogen and one's extending back towards the other hydrogen. And that leaves behind this p orbital. All right, that p orbital, which is the unused atomic orbital around the carbon, right? Leaves behind that p orbital. Well, what happens is that when these two bonds come in close proximity, the two hybrids, close enough to form a bond, right? Whoops, these two orbitals come close enough to form a bond. The remaining p bonds begin to overlap as well and form what's called a pi bond. And that pi bond occurs above, because of the lobe of electron density that is remaining on both those carbons, and below, because there's electron density that remains below. All right? They're called pi bonds because pi is the Greek letter for p, and these are p orbitals forming a bond. All right? So what this is represented by the, let's see here. The way we represent this is we draw two bonds, right? One of these bonds then represents an overlap between the hybrid orbitals, but the other one represents an overlap between what, Chad? What does that second bond represent an overlap between? You there, Chad?
Yeah, I'm here. When I think of the two bonds, I think of the pi bond, but I know that's completely wrong.
What do you mean? What do you mean you think it's wrong?
Well, I think the double bond means pi bond. Is that wrong?
No, that's not wrong. That's not wrong. One of the bonds in a pi bond is, one of the bonds in a double bond is a pi bond. That's right. The other one is an overlap between these hybrid orbitals. So why do we call it a pi bond, Chad? What is pi? What's pi come from?
Isn't it the circumference from a circle?
Well, they called it that in math. Yeah, that's right. But I mean, it just happened to be the letter that they were interested in, right? P.
Mm-hmm.
Pi stands for P. And so we call this a pi bond because it's an overlap between p orbitals, the remaining p orbitals that are not involved in creating hybridized orbitals. Does that make sense, Chad?
Yeah.
Okay. So, what kind of bond is occurring, Brielle? What kind of bond is occurring between the carbon-hydrogen bond here, the one that I'm drawing here? Carbon is extending what kind of an orbital towards that hydrogen bond? Do you know, Brielle?
I'm not sure, but is it the s orbital?
Carbon is extending a hybrid orbital here. Does that give you a clue?
Yeah.
What is it? What kind of orbital is being extended from the carbon? It's this sp2, right?
Yeah.
Does that make sense? Carbon is extending the sp2, and we can see it here in this drawing. Hydrogen is extending what, Brielle? What does it look like? What is hydrogen using to overlap with that sp bond or sp2 hybrid? It's just extending its s bond, or sorry, its s orbital, right?
Okay.
Because that's all it has.
Mm-hmm.
So this bond is an overlap between an sp2 hybrid orbital from carbon and an s bond from hydrogen. Okay? So these bonds and one of these double bonds, right, are bonds from extended sp2 hybrid overlap or hybrid bonds to hydrogens or to other sp hybrid hybrid bonds or hybrid orbitals here. So bonds that are either hybrid overlaps or s orbital overlaps are called sigma bonds, where sigma is the Greek letter for s, right? Whereas, again, our overlap between remaining pi bonds are called, or remaining p orbitals are called pi bonds. Okay, so let's see. Here we have a compound. Whoops. See this compound, Landon? C2H2. All right. We'll draw it here. Just like it's drawn up at the top there. C2H2. All right. And we have a triple bond occurring between these two carbons, Landon. What do you think? Describe what's going on for those three bonds. Why do we have three bonds, and what kind of overlap is occurring in those three bonds?
I know what you said in the double bond that one of the bonds was a pi bond. Is this a triple bond because there is one pi bond, one sigma bond, and then one D bond?
Okay, very, very good thinking. It's actually, you're right, that one is a sigma bond, all right? So let's think about that. Let's answer that question. What is the hybridization around this carbon, Landon? Do you know? What's the hybridization necessary around that carbon?
It'd be SP.
That's right. It's sp hybridized. Sp hybridized. It took an S and a P and extended two regions of electron density to its neighbors, but that means it left behind, this time left behind not just one p orbital, but two p orbitals. Two p orbitals. And so when you get an overlap between the two sp hybrid bonds, hybrid orbitals, there also can result an overlap between the remaining two p orbitals and result in two pi bonds. Does that make sense, Landon?
Yeah, that makes sense.
So describe to us now, what do these three bonds represent?
So, from my understanding, there's one sigma bond and then there's two pi bonds.
That's right. And what? Keep going. Yeah, going good.
Right. I was saying the two pi bonds come from the leftover orbitals from the p orbitals that were helping bond the carbon and the hydrogen.
Good. Very good.
Just around the carbon atom, I should say.
That's right. Okay. Very good. Now, one last thing. This is kind of the critical thing that all of that was leading up to. This one last thing. Because of that, bonds that contain pi bonds cannot freely rotate. Bonds that contain just sigma bonds can rotate. And you can visualize that pretty well with these molecules. So for example, if I were to grab this carbon right here and try to spin it, spinning this carbon would make these hydrogens spin around, and this carbon here, I could spin it as well, would make these hydrogens spin around, but that wouldn't decrease the amount of overlap that I have from this sigma bond. However, if I took this carbon and spun it, it would ruin the overlap that is associated with these pi bonds, because the pi bond overlap is depending on the fact that these orbitals are aligned appropriately for each other. If they switch like that, then you can't get the bonding because there's no longer an overlap that can occur. And what that results in is, again, like I said, sigma bonds can freely rotate, but any bond that contains a pi bond cannot rotate because you have your p bonds lined up, and those p bonds, those pi bonds, have to stay lined up to maintain their bond. All right, excellent. So that is the information from Chapter 10.